Okay, good morning, calculus class. This is Mr. Kong. I wanted to talk to you a little bit more about the derivatives of inverse functions in section 3.6. I think yesterday I kind of let off a math bomb in the middle of the room, and a lot of you were left dazed and confused, and some of us with negative comments, Sammy. Anyway, so I thought I'd try and re-explain this. All right, so we know what an inverse function is. We know what its relationship is to the original function. We know how to find the inverse. So how do I find the derivative or the slope function for that inverse? Let's take a look at an example. I want to find the derivative of the inverse, and then I want to find the slope of that inverse at a given value a. All right? Well, in this method 1, what I'm going to do, let's see this method 1 here, I'm going to use the old switch and differentiate idea. Now, we know that the we know that the inverse of a function is simply when you switch the values x with the letter y, right? So this equation here is the inverse of my original function. Agreed? Now, I could differentiate this right now using implicit differentiation, but I think it's going to be pretty easy for me to get y alone. So I'm going to get y alone now. I would subtract the 5. I would divide each term by -2. And then finally, wouldn't I just cube root both sides to get rid of that cube? So I know that the inverse function would simply be the cube root of -1/2 x plus 5/2. Okay? Well, now I've got to find the derivative of this inverse function. Okay? So to find the derivative of f inverse, and this is how I'm going to write it, well, again, I'm going to take the derivative of this cubic function, all right? Cube root function. And again, I know I got a little bit of chain rule here, so that looks like a little bit of 1/3 times the inside raised to the -2/3 power times the derivative of the inside, which would just be -1/2. Cleaning this up, I would get the derivative of my inverse is, I believe that would be -1/6 times the cube root. Actually, I'm going to pick this at 1 over the cube root of -1/2 x plus 5/2 and then squared. Okay? Now notice I could have squared the radicand, or I can put the squared on the outside. I think it's easier to square or to cube root first and square later. Okay. Alrighty. Now that I've done that, I think I just need to plug in that given value for a in for x, right? So to find the slope of my inverse, at x equals 7, I was told that a is 7, but a is x, right? This is the same thing as x, right? I would just go -1/6 times 1 over the cube root of, let's see here, that's -1/2 times, let's see here, 7 plus 5/2, all right? And then squared, all right? So actually I'm going to write a little bit bigger here. So I get f inverse derivative at 7 would be -1/6 times, let's see, in my radicand here, I've got 7 times -1/2, which become -7/2 plus 5/2 and then squared, all right? Which would give me -1/6 times 1 over, let's see here, -7/2 plus 5/2 is just -2/2, or just -1, and then squared. So that would be -1/6 times, well, wouldn't that just be 1? So my derivative is just going to be -1/6, and that's my answer to this problem. Okay? Now, again, so how did I evaluate this derivative at that given value? Again, I found the inverse by switching x and y. I then isolated the y because it was easy to isolate, and then I took the derivative, and then I evaluated. I think that's pretty straightforward. It's very similar to what we've been doing. Okay, let's look at a harder example now. Okay, for this next one, I've actually taken this problem straight out of your exercises. I'm given the rational function f of x equals x plus 3 over x plus 1, and I only want to consider the domain of x greater than negative 1. Okay. Now, I want to find the derivative of this and then evaluate that derivative at a equals 2. Well, let's see here again. To find the inverse, I first need to switch x and y. Now I want to try to isolate y. Well, let's see here. To isolate y, I would get rid of that fraction. I'm not a big fan of the fraction. Since I need to isolate y, I need to group my y's together. So I'm going to subtract my y term on the right across and then get rid of that x on the left. Factoring the y out of both of those terms, I get this. And lastly, dividing the quantity of x minus 1 across, I get negative x plus 3 over x minus 1. So I know that my inverse function would be negative x plus 3 over x minus 1. Okay? Well, again, now I want to take the derivative of this function. All right? Well, again, it looks to me as though, well, I could do this in one of two ways. I want to rewrite this problem as a product rather than a quotient. All right. So let me redo this. I'm not going to take the derivative quite yet. I could say that let's see here. I know that this would be the same thing as the quantity negative x plus 3 times x minus 1 to the negative first power. Correct? Now let's find the derivative. I think it's easier. I find a lot of students are enjoying, shall we say, this method better. So the derivative of the first factor would just be, let's see here, negative 1 times the second factor, which is x minus 1 to the negative 1, plus the derivative of the second factor will be negative 1 times x minus 1 to the negative 2 power times negative x plus 3. Agreed? So that's my derivative, all right? You know what? I'm going to clean this up just so that we can get some practice on this. I know that that will be, I don't know why my tablet keeps doing this. I know that in this factor has an x minus 1 to the negative first power. This factor has an x minus 1 to the negative 2 power. So I can factor out the smaller quantity of x minus 1s, which would be the x minus 1 to the negative 2, from each of these. And I would be left with, well, the first term would be left with just negative 1 times, well, let's see, if I take out a negative 2 from a negative 1, well, negative 1 minus negative 2 becomes, well, golly, I think just x minus 1, right? To the first, if you want to put a first, but I don't think we really need the first power, right? Okay, so I'm going to get rid of that. And then let's see here, if I took the x minus 1 to the negative 2 out of the second term, I would be left with plus a negative 1 times negative x plus 3. Okay. Well, from here, let's see here. I can do a little bit of math on the inside. I can get x minus 1 to the negative 2 times negative x plus 1, and then plus x minus 3. Okay? Which becomes x minus 1 to the negative 2 power. Let's see here. I think the x's cancel, and I'm just left with times what is that? Negative 2? Wow, that really simplified nice and pretty, didn't it? Okay. And so now I'm ready to evaluate. Let's see, I wanted to evaluate when a equals 2, correct? So now I'm just going to plug in a 2 for this x value. So I get 2 minus 1 to the negative 2 power times negative 2. Well, again, the 2 minus 1 is 1, and 1 to the negative 2 power is still 1, and 1 times negative 2 is simply just negative 2. So, sorry, that's an apostrophe, of 2 is negative 2, okay? All right, ladies and gentlemen, now let's take a look at an even more difficult problem where it's going to be hard to isolate the y. Okay, so let's take a look at this problem. I've got y equals x cubed plus 2x minus 1, and I want to find the derivative of the inverse of this function and then evaluate that at the given value of 2. All right? So the first thing I want to do, well, let's switch the x with the y. Okay, now for all intents and purposes, this is my inverse function, right? This is my inverse, okay? It's just not written with y explicitly written in terms of x, right? So now I know I want to take the derivative of this inverse function and then plug in 2 for x, right? Well, to do this, I'm going to have to differentiate implicitly, right? That's where our old friend implicit differentiation can help me out, all right? So the first thing we do to take the derivative of this, let's see, I take the derivative of each term. The derivative of x is 1. The derivative of y cubed is 3y squared. But don't forget, when you take the derivative of a y term, you always have to attach a y prime. Plus the derivative of 2y is 2y prime. And the derivative of negative 1 is 0. Okay, now that I've taken the derivative of my inverse function, I need to isolate y prime. Well, to do that, and again, this is just algebra, I get y prime equals 1 over 3y squared plus 2. Again, I just factored out the y prime and then divided the quantity 3y squared across, plus 2 across, all right? Now it's time to plug in the 2. So I'm going to plug in this 2 for x in this. Oh, golly. Guys, I know that this has to go in for the x of my inverse. But there ain't no x. Ain't no x in this. Oh, what do? Well, again, I know that for this inverse, I've got this value of 2 for x, comma, some y value. Well, again, I need a y value to find this derivative. Well, again, how could I do that? Well, I know that x is 2, so couldn't I plug this 2 in for this x in my inverse function? Again, this, folks, this is my inverse function. Well, if I did that, I get 2 equals y cubed plus 2y minus 1. Again, because this is a higher order equation, I have to make one side 0. And then solve. Now, here's my issue. Guys, be careful. This is a y cubed, not a y squared. I cannot factor this guy like I normally do. So, well, this doesn't factor, so what could I do? Well, I could graph this function out and then see what the x-intercept is, since I know I want it to be 0, right? Well, if I did this, I would get I would get y equals 1. So again, I know that when x is 2, y would be 1 for my inverse function, right? Now that I know that, y is 1, now I can plug this into my derivative and evaluate the derivative at y equals 1. So I get 1/5. Okay? All right, and that's where we can, again, we can use our old understanding of inverses. We switch the letters x and y. All right? If we can get y alone, get y alone. But if not, then we differentiate implicitly. And then in this case, since my equation was written in terms of only y, I had to find the y value to plug in using this x value here. So again, we plug that x value into x in the inverse function and solve for y. Okay. All right. Now let's go to the derivatives of inverse trig functions. All right. So the derivative of inverse trig functions. All right, I'm going to try to take this a different approach. I've given it some thought here. So let's take a look. Suppose I'm given the function y equals sine of x. All right. Well, again, how do you find the inverse? Don't you simply just switch x and y? So wouldn't I get x equals the sine of y? All right. Well, again, to get y alone in this inverse, don't I have to move the sign from the right side to back to the left side? Well, we're not actually moving it. This is something that probably was kind of glossed over in your geometry in Algebra 2 days, but I'm going to talk about it more. Again, I know that to undo a function, I just apply the inverse function. So you see how I've got sine of y here? If I wanted to undo this sine away from the y, well, couldn't I just apply the inverse of the sine? So couldn't I take the sine inverse of the sine of y? If I do that, does it make sense that those cancel out? Basically, they're opposites, they're inverses, so they cancel, right? But again, if I took the sine inverse of the left, wouldn't I have to take the sine inverse of the right? Or vice versa? So if I wanted to get this y alone, I'm going to take the sine inverse of both sides. All right, leaving me with just y. Now, notationally, as I said, instead of sine inverse, we can also rewrite this as the arc sine of x is equal to y, right? So this is the inverse function of y equals sine of x. Now I'm going to take a look at the derivative of this guy. Okay, now to take the derivative of this guy, I don't want to sound like I'm chasing my tail here, but I'm not real comfortable with arc sine. So I'm going to rewrite this actually, moving the arc sine back to the left side. Again, wouldn't y equals arc sine of x be the same thing? And I just said this as the sine of y equals x. Again, I just wanted to kind of show you that this is what the equation of the inverse of sine looks like, right? Okay, so to take the derivative of sine of y equals x, right? Again, don't I just differentiate implicitly here? Well, let's see, the derivative of sine of y would be cosine of y. But again, if you take the derivative of y, you always attach y prime, equals 1, right? So doesn't that mean that the derivative would be just 1 over the cosine of y? But in this case, you see how I get this y here? Folks, I want my derivative to be in terms of x. So I need to somehow get some x's in this problem, right? And in fact, what I'm actually going to show you is how I can get rid of the y, but I can also get rid of the trig functions, right? I'm going to go back to this equation right here. Sine of y equals x. Guys, in this equation, it says the sine of this variable y is equal to some x, right? Well, whenever you have the sine of some number, you know that this number has to be an angle, an acute angle in the right triangle. And I also know that that always equals some ratio, right? So this x must be some ratio of the two sides of a right triangle. Now again, since it's a ratio, I need to make this into a fraction, right? I know that the sine, by definition, is the opposite side over the hypotenuse. Well, what number could I put on the bottom here so that I don't change this fraction overall? Couldn't I put a 1? So I know that my opposite side to the y angle is x, and I know that the 1 must represent my hypotenuse. So at this point, let's drag in a right triangle, right? And let's label what we know. Well, let's see here. I know that my angle is y, so I'm going to put a y there in my right triangle. I know that the side opposite that angle is x, and I know that the hypotenuse is 1. Well, wait a minute. You see how in my derivative I have y prime equals 1 over the cosine of y? Well, gosh, using this right triangle, don't I know that the cosine of y is the side adjacent to this angle y divided by the hypotenuse, which is 1? So if I could somehow figure out this adjacent side in terms of x, I could say it's this side over 1 and replace that with cosine of y. Well, again, couldn't we just use our old friend Pythagoras to say that, let's see here, if that's a, doesn't a squared plus x squared have to equal 1 squared? Right? So wouldn't a squared equal 1 minus x squared? So doesn't a equal the square root of 1 minus x squared? Right? So I know that this adjacent side is just the square root of 1 minus x squared. Well, because of that, I know that I can just say that the cosine of y, coy, don't be coy, cosine of y is just adjacent over hypotenuse, or just the square root of 1 minus x squared, right? Well, again, now that I know that, couldn't I replace this cosine of y that in my derivative with that with that value? So I know that y prime is equal to 1 over the square root of 1 minus x squared, right? All right, so I've shown you how it's derived or how I got that. So now let me just clean it up and let's see what we know. If I'm given the inverse function y equals arc sine of x, then I know that the derivative of this function is, well, I believe I got 1 over the square root of 1 minus x squared, right? All right? Well, now let's extend that and use a little bit of a talk of chain rule. Well, again, what if instead of an x here, what if that was some complicated x expression? Well, you can always hear me reference that as replacing that with u, right? Well, again, if I want to define the derivative of some inverse trig function like arc sine of u, where u, again, represents some x expression, well, the derivative of that function would be, well, the derivative of arc sine, which is 1 over the square root of 1 minus, and instead of x, it would be u squared, times the derivative of u, right? Or simply 1 times u prime is u prime over the square root of 1 minus u squared, right? Right? Okay. Now, again, to help ease the memorization of this, I'm going to use some notation that I've referenced in the past. So if I want to take the derivative of the arc sine of u with respect to x, that just simply equals this expression here, u prime over the square root of 1 minus u squared. Okay? So let's take a look at some of the problems out of your exercises. Okay, this is number 23 out of your textbook. This is find the derivative of the function. I'm given the function equal to the arc sine of x plus 1. All right? So to find this derivative, I first say, well, okay, this is my ratio x plus 1. That's my u value. So I know that u prime is equal to, well, the derivative of x plus 1 is just 1. Okay? And so the derivative of this function would simply be u prime, which is 1, over the square root of 1 minus u squared. Well, u is x plus 1, so wouldn't that just be x plus 1 squared according to my formula? My formula again being u prime over the square root of 1 minus u squared. And I've just taken the derivative of that function, right? Now, if I wanted to, again, slightly clean this derivative up, I could actually do some algebra. So the derivative would be equal to 1 over, again, x plus 1 squared in my radicand here would become 1 minus the quantity x squared plus 2x plus 1, agreed? Which then would become 1 over the square root of 1 minus x squared minus 2x, let's see here, minus 1. The 1's cancel, so my overall derivative is just 1 over the square root of negative x squared minus 2x. Now let's take a look at the derivative of the inverse function arctan of x. All right, now I know that this function was produced already by taking the original function y equals tangent of x, switching x and y, and then isolating the y, right? We know that, right? But I want to find the derivative of this inverse function now. So again, I feel more comfortable without the arctan in the problem. I feel more comfortable with tangent. So my first act will be to move the arctan back to the left and create just tangent of y equals x. Taking the derivative of both sides, I get, let's see here, what is the derivative of tangent of y? I believe it is, let's see here, secant squared y prime equals the derivative of x is 1. So wouldn't y prime equal 1 over secant squared y? But again, I don't want my derivative written in terms of y, and in fact I also want to get rid of the word secant, right? So to do this I need to draw a right triangle, okay? Using, again, this equation, I know that y must be my angle, so put y here, and this x must be the ratio of sides that are adjacent and opposite, correct? Let me get rid of that little circle here. This ratio of this x must be the opposite side and the adjacent side to my angle, right? Because definition of tangent is opposite over adjacent. So that would be x, that would be 1. Again, to find the secant of my angle, well, wouldn't that have to be, well, let's see here, the definition of cosine is adjacent over hypotenuse, so wouldn't the definition of secant be hypotenuse over adjacent? So I need this hypotenuse here. Well, again, through the magic of the Pythagorean theorem, I think, well, actually, no, let me just show it. Wouldn't it be 1 squared plus x squared equals c squared, where c is my hypotenuse? So doesn't c just equal the square root of 1 plus x squared? You could also put x squared plus 1 if you wanted to, right? So, if this is the square root of 1 plus x squared, I know that the secant of y is equal to just the square root of 1 plus x squared, right? Well, if I plug this in over here, don't I get y prime equals 1 over the square root of 1 plus x squared. Oh, wait a minute, that squared says I got to square this quantity. So wait a minute, that just cancels. So I get y prime equals 1 over 1 plus x squared. So I know that the derivative of the arctangent is equal to this, right? Well, in general, we can say, again, instead of some x, if I have some x expression, if I have y equals the arctangent of some x expression, say u, I know that the derivative of the arctangent of u in terms of x will equal, well, again, I have to take the derivative of my my ratio u prime and divide that by the 1 plus u squared. Okay? Right? Now, if you look at your textbook, there's a nice handy-dandy little summary of the derivatives of all my inverse trig functions. I want to show you that now. All right, as you can see on page 176, this little box of knowledge here, this derivative of inverse trig functions, this summarizes all 6 derivatives. Now again, I showed you how we got arcsine of u and arctangent of u, but here's arcsecant, arccosine, cotangent, and cosecant, right? I do want to give you a little mnemonic device or helpful hint. If you're taking the derivative of any of the functions that begin with the letter c, if you take a look at this, they're the exact same derivative as sine, tangent, and secant. The only difference is, isn't the numerator just negated? So instead of u prime, it's negative u prime, right? So you don't have to memorize as much. The reality is probably on this AP that, the two that they emphasize the most are the sine and the tangent, and that's why I derive those. Okay? Now let's take a look at your book, and let's take a look at some problems that they've done for us in some examples. Okay, here are 4 examples, again, taken out of your book on page 176. All right, if I want to take the derivative of this inverse trig function arcsine of 2x, well, again, this ratio is my u value here is 2x, so u prime, I know, is 2. Well, according to my rules, the derivative of this will just be u prime over the square root of 1 minus u squared, right? So they plugged in u here. So you just get 2 over 1 minus 4x squared. Okay? Again, the derivative of arctan of u, we said was just u prime over 1 plus u squared. So again, if I have arctangent of 3x, again, the derivative of 3x is just 3, that's my numerator, over 1 plus u squared, so 1 plus 3x squared is 1 plus 9x squared. All right? Arcsine of square root of x. Again, the derivative of square root of x is 1/2 x to the negative 1/2. I think we can all see that numerator. Over 1 minus u squared. Well, the square root of x squared is 1 minus x. I hope we can all see this, right? Now again, what they do is so they don't have complex fractions, they move the half and the x to the negative 1/2 to the denominator and just 1 over 2 radical x square root of 1 minus x. Well, wait a minute. We know that numbers inside the house can play together, so this square root of x can be distributed into this other square root, and so x times 1 is x, and x times x is x squared. I hope we can all see that answer. Again, let's look at another one where we have arcsecant of 2x. Again, applying the formula for the secant, the arcsecant function, right? The derivative of u, well, again, in this case, isn't u this e to the 2x? Well, again, does it make sense how we got 2e to the 2x is u prime here? Over, again, if you look at the formula, it's just whatever u is times u squared minus 1. Okay? And so they got this as their derivative. Simplifying, I think we can see that, let's see here, doesn't e to the 2x and e to the 2x cancel? Right? And then e to the 2x squared is e to the 4x. So I hope we can all see how I got that. Okay? Guys, I truly I hope that this was a better explanation. I promise I won't let it happen again, Sammy. Bye.